Thanks for having me. My name is Professor Cheng. So I'm Chair of Intelligent System Modeling and Simulations. I'm going to give the presentations on intelligent acoustic classifications and detections. So I'm from Newcastle University, Singapore. So my research area is in intelligent system design of complex systems. And you may ask me what do we mean by complex systems, because in systems there's many types of systems in the world. Okay, or even in our research areas. So I'll just look into the battery, acoustics, and the vehicles. So you can see that the intelligent system have a lot of challenges. Okay, so you can see that there's a lot of data, a lot of storage, external disturbance, and its time variance and model uncertainties. We will see that the research project surrounding this circle that I'm doing is mostly a lot of hands-on and deal with the actual systems. I have a lot of EDVIPP. Currently I have a total of 9 and 2 SMI, Singapore Maritime Institute projects that I've been through. So today the content is on the acoustic scenes classifications, acoustic sound event detection. So first part on classification, second part on the event detections. So information in everyday soundscapes. On the left hand side, you can see that if you go into the busy streets, you can hear a lot of sound. Right, a sound coming from the car, from the pedestrian, even from the building itself, and even from the animal that walk past. So the entire scenes is what we call the scenes, or sometimes environments. Okay, we can say that this is the urban environments. Probably is another case is forest, and also the office. And this is what I call the acoustic scenes classifications. So for individual sound or sources, you will see that we want to detect the sound events. Let's say there's dog that's barking. We want to know from what time to what time. And the car horn also from certain time to the end time. Alright, so we can say that this is onset and this is offset. And this is what we call it's a sound event detection. So from very general to very specific. Okay, this is what we mean by classification and detections. So for acoustic scenes classification, you will see that the whole scenes is characterized in one labels, right? It can be pedestrian street or can be city center. This is just a few examples of the scenes label that we use. It's not restricted to all this, but it's just a few examples which I try to show here. And for sound event detections, if you recall that I mentioned you try to estimate the start and end time of the target sound classes. Okay, you will find that this is what I call the detections. And like for example, given a sound in a wave format, you will find that going through the algorithms, you can determine the footsteps, start and end of footstep, and then pause for a while, and there's another footsteps. And at the same time, there's overlapping sound from someone that is talking, and probably from your house, there's some car that drive past. All right, so these are the sound that overlap with one another. All right, so we will see that it's multiple classes, and the sound overlap with one another. Okay, so this is just an examples that human talking from let's say 0.5 seconds to 1.2 seconds, and the car horn from 0.8 seconds to 1.4 seconds. So there's a lot of example on sound event labels, like for example, these are all the sound event under the kind of different kind of scene. For example, in the forest, in the urban setting, and so on. So another terms that we want you to understand is the monophonics and polyphonics, SED, sound event detection shorts. Okay, for monophonics, SED, you will find that there's no overlapping sound, like dog barking followed by alarm. It's very clear differentiation. All right, but for polyphonics, you will find that there's dog that is barking, but at the same time, there's someone that's talking. We label as speech. And then pause for a while, and there's someone talking, and then suddenly there's alarm. Alright, so this is something that is more realistic. The later one is more realistic because that is the real life kind of applications. As there's many audio clips, it's more likely to contain multiple and overlapping sound events. Okay, so there's another term that we use is the tagging with labels. Okay, when you talk about tagging means that let's say given a sound, okay, in the time domain, okay, we can differentiate. Say the first part of the sound is cheering with the timestamp, start and end. Laughing followed by barking and gunshots. So this show a very strong labeling of event, strong labels. Okay, conversely, when I talk about weak label is we do not know the start and end of cheering, laughing, barking, and gunshot. We give you just one single label that it contains all this. It's not in sequence, it can be in different sequence. Okay, it can be gunshot followed by laughing, cheering, and barking, and so on. So this is an illustration of bit labelings of events, no temporal informations, multi-label classifications, and this means that there's multiple class that can be active simultaneously. So application-wise, in context-aware devices, you can find that there's hearing aids, anything that deal with sound, it can be used, even smartphones, and even autonomous car. Nowadays, even you try to detect what is the driving behavior of the drivers, you'll find that you use a smartphone now, okay, because it can actually serve as microphones, and it can also show, okay, what is the kind of GUI you want to display, and how you can provide this information to the insurance, okay, just in case that when you are sleeping and you get into the accidents, this insurance company will be aware of that, right? They will know how to make the claim. All right, and also for acoustic monitorings, okay, like for example, baby cryings, window breakage, the bird sound detections, and it can be used for environmental kind of monitorings. And for application like assistive technologies, for example, automatic captioning, okay, this is something that has been done. Provide videos, I can provide captions for you. All right, so this is something that has been done for many years. So as compared to other audio processing field, like for example, speech and music, okay, these acoustic scenes classifications and sound event detection is not that mature as compared to speech and music. Okay, so what do we mean? Definitely we look at some of the similarities. You will find that for acoustic properties, where we have different type of inputs, definitely different type of features that we can extract. Usually it's a spectrogram, because the log mu spectrograms, okay, is more closer to our human listening kind of frequencies. So we use a log mu spectrogram more often than others. All right, and then we can go through a separation into the harmonics components and the percussive component as well. All right, so similar acoustic features that we very oftenly try to gather is the log mu energies, okay, or the log mu spectrograms. And what are the common tools that we use is the CAN, fuzzy neural network, recurrent neural network, which is a mix of the CAN with the IN, and the Gaussian mixture model, hidden macro model as well. Okay, these are some of these very typical kind of wave file that we see in the time domain, and on the right is the frequency domain. And the density of this determines the level of dB in this spectrogram. So the difference is that there's no established taxonomy, okay, of event and scenes. Okay, it's not as common as compared to these music and speech. So in many typical these examples, when we compare this with music, which always the mic is very close to us, right? No one sing very far away from the mic, and then no one speak very far away from the mic. So as compared to these acoustic scenes classifications or even event sound detections, you will find that we tend to collect the sound from very far away. All right, there's no way that you can, try to attach a mic to the dog, right? So, or to the car, all right, and so on. So the transfer function from the source to microphone can be a problem because we have a low signal, all right, to noise ratio. We often want to have a high signal as compared to the noise, but in most cases we couldn't achieve. All right, so the SNR is here is just to show you how we calculate. Okay, is this one the pressure sometimes from the mic is sometimes in Newton per meter square, but we convert that into the logarithmic. So we use a log base 10, and then we actually do a P signal over the P noise, and we determine what is the sound in terms of dB, decibel. Okay, so the difference you can see that is environment sound is often less structured as compared to the music and speech. There's a certain structures, right? And there's a lot of independent source, okay, background noise, okay, from different sources. And all these have different type of acoustic characteristics. Okay, and the available data set, as I mentioned, is always smaller as compared to the speech and music data set. Okay, so I mean for speech, there's entire things that we can look into. Also in terms of music, we can look into that as well. For a general machine learning approach, based on supervised learning, the set of possible sound classes defined in advance. So we need to have a annotation or annotated training material from all classes because we are looking at the supervised learning. And we have this algorithm, let's say for examples, given what is the sound or wave file, and we can detect what is the footstep, start and end, and then followed by speech and the car. All right, so we can have we need to have a label data set, whether is it a strong label or a weak label. Okay, the general machine learning approach, there's audio feature extractions followed by acoustic features, and then we have the basically get a different type of acoustic features like spectral centroid, spectrogram, mu spectrogram, zero crossing rate, and spectral roll off. Okay, where we can actually classify or characterize the kind of sound that we obtain and go through the machine learnings. And this is a process where methodology of training models using data set is being in place. And what is the three tasks that we can get from here is that first thing we know classification. We can class this as a busy street for example, and we can even do the tagging. Okay, meaning that given this busy street, okay, I know that there is a car horn, footstep, talking, sirens, right? And not only that, we can even tell you that, okay, car horn start at what time and end at what time. So start and end, and footstep start and end time. Okay, so we can see that from very general into more specific sense. Okay, so this is just an example of scenario. Let's say you have some, if you happen to go to the forest or wildlife reserve, you'll find that the recording might be classified as a nature sound, and the recording might be tagged with labels. Okay, means that tagging means labeling. Okay, like a bird sound, wind, rain, animal call, and so on. Okay, and we do detection. If you want, the system might detect the specific event, let's say a bird call at a certain time and end at a certain time. So sometimes they give the durations and the start time, so you can work out what's the end time. Okay, that's depending on how you want to look at the data set. And the rain start at certain time and end at certain time, and so on. Right? So from very general sense to more specific, we want to know the time that it start. So we put a temporal information there. So for training stage, we optimize the acoustic model parameters to minimize the loss between the predicted and the target output. So you can see that there's acoustic features. So it's the acoustics model. We want to, this is something that means that we already done the training. So we have the acoustic model. So we have a loss function because we want to find out what's the errors. And we have this target output compared to the acoustic learn or from output from this acoustic model. And then we know what will be the final outcomes. Right, the acoustic feature as mentioned, there's a lot of them. There's an audio signal, there's a mu spectrograms. Okay, and this is just an illustration, okay, of one of the features called mu spectrograms. Okay, it can be a spectrum centroid, or even spectrogram itself, zero crossing rate, spectral roll-off, and so on and so forth. There's many different ways to classify a signal. Okay, when I say signal, it's an audio signal. Convolutional neural network (CN) is pulling a lot of the learning of the shift invariant features. So you can see that for CN, you have convolution, max pooling, or sometimes they have more than one or two layers. All right. So basically, these multiple CN layers will allow the learning of high-level features. Okay. So this is a traditional approach that you see just now. So you will see that the top one is I mentioned. Is we can actually have an end-to-end approach that the system taking the raw audio signal as an input and directly output the classifications or detection results. Okay, with the neural network learning both feature extraction and classification simultaneously. Okay, so it's possible to combine CNN with RN. Okay, so we can see that this whole network will be optimized simultaneously to give the CRAN. So for classifications, this is the task that we will be doing. First thing is audio feature extractions and get the feature metrics, which often in terms of metrics, if the features get larger, the metrics get larger as well. Okay, so you have this go through the machine learning process and the algorithm that we're using. And for this, we have these annotations. We need to encode this into a target output that can be used in the computer so that you can make the comparisons. And that will give us what we call the acoustic model. Okay, which is the learn model that we have. And for the inference stage, okay, meaning that is the what we call the deployment stage on the unseen data set. All right. So we also do feature extractions. We create the inputs, which is in terms of metrics, do recognitions, and give the system outputs. All right. So in terms of the usage stage is a context of machine learning, okay, which is a retrained and validated model is being deployed. Okay, so actively used to make predictions, okay, on unseen data set or a new data set. So for audio taggings, which is multi-label in nature, the top row still remain the same: audio, feature extractions, feature metrics, and what I call the machine learning approach. Here now, because of the multi-label nature, we have speech, music as the annotations, and we do the multi-label encoding so that the computer will see as exactly that one want to see. Okay, so this is the target outputs. Okay, for it to learn and get the acoustic model. Okay, so for inference stage, we have audio, feature extraction, input recognition, and now you can see there's the tag activities. Okay, probably speech or and music. Okay, for detection wise, we know that we have sound event detections, temporal activities estimated along with the class label, which is class A, B, and C. So class A can be a dog barking, B can be a speech, C can be car horn, for example. So it can happen at different time, and it can pause for a while, and it can happen again. So if we can divide this audio into frames, and depending on the resolutions, the more frames we can divide, but we need more time, right? So if we can divide into a certain number of frames, and we know what is the start and end time. It may not be exact depending on number of frames that we divide. Okay, so it's what we call the multi-label classification in this case. So here for sound event detections, we still have the same thing like learning stage: audio, feature extractions, feature metrics, and go through a machine learning approach. Okay, and then here we have annotation with temporal information. Okay, the start, the onset and offset, start and end time, and go through a multi-label encoding so that the computer will see, okay, what type of target output that you have, and then we do comparison, the loss function, and get the acoustic model. Okay, so this basically inference stage, we have the audio, feature extraction, input recognition, and now you can see the binarizations of class, present, probability done at the frame level. Okay, so in the frame level, you can see the vertical stripe that we have is in the frame level, and the horizontal one is all the tag label, like for example, speech, car horn, and dog barking, for example. So there's a lot of approach like few shot learning architectures. Why we want to do that? Because the conventional ways of collecting the data can be laborious and difficult to annotate large amount of data. Okay, it's very challenging for supervised machine learning techniques. So you want to look into a few label data set. All right, so we want to learn from few examples, and we need real-time and on-the-fly detections. So we have 5 classes of, let's say for this few shot learnings, 5 classes. You can see 5 different colors. And there's 2 shot because you can see a stack. Okay, there's only 2 stats, so 2 label example per class. So we have training data set, and this is what I call the support set. All right, so these episodes typically contain, let's say, one episode contain the support set and the query set. Okay, query set is often unlabeled examples. Okay, so you will see that we have also the CN, so we have log mail spectrograms, there's input batch normalizations, and convolution max pool, convolution max pool for 3 times, flatten it, and this basically our 4 CN blocks. Okay, for this GSIN, for this case, all right, is we have a few shot learning methods such as the metric-based few shot learning methods such as the prototypical network. Okay, this is what we employ. There's many type of these few shot learning methods, but we just deploy this basically using the square Euclidean distance. Okay, so here is the overall entire system, how it look like. We have support set, we have labeled as positive because this is the target that we have, and then we have queries frame, which is the something that we never see before. So we just divided it then in frame, and then we say that, okay, is this positive equal to negative, and go through the few shot model to get the predictions. Okay, so we only have 1 target. Okay, a very few target because we have only a few samples. All right, another one common one is transformers. Okay, it's basically a backbone CN is being used to extract the feature of the map. So CN is very good in extracting the features. Okay, from any image, like for this case is the spectrograms, and this map is combined with the positional encodings and feed into the transformer encoders. Okay, and then we have transformer and decoders. okay, which use the n+1 embeddings, okay, to basically generate what I call the creep level, which is the scene level, and then we also have the tagging as well as the event detections. Then we fuse the whole result together, give the outputs. All right. So for transfer learning, if you don't use few shot, you don't use what I call the transformer, we can use transfer learning because we work on a small target data set. All right, because we can fine-tune the pre-trained model. Okay, we just download the pre-trained model in the smaller and label data set of the environment sound. Because it's less time consuming as compared to we collect ourselves. All right, so we have only small data set, and in this case, for transfer learning, we use this Google audio set. All right, and then we have source model and do the extract the embeddings. All right, it's basically discriminative representation of data by mapping it into the n-dimensional vectors. Okay, it's all vectors and metrics, and go through the machine learning methods, and then you get the target model. And you may ask the data set, as I mentioned, we have a weak and strong data set, right? So weak data set means that we don't have the start and end time. We only have the speech, okay? So here, strong data set means that we have on and offset. So it poses some challenges. Why? Because a lot of time we can have a different onset. It's very subjective, okay? We know that probably start and end, depending on the resolution that we want. But some give a more conservative one. So you can see the onset is a bit wider, have a wider window as compared to the one on the left hand side. So there's many possible onset offset positions. So very subjective. And these are some of the few examples of data sets, TUT acoustic since 2017 and TAU urban acoustic since 2019. And there's many other data set, and the audio set, which is something that is very commonly used, and it's always getting larger and larger. So TAU urban acoustic since 2019, you can see that someone collected all these by professionals, and it's very high quality mobile device. But for TUT sound event data set, I want to differentiate is that sometimes they merge the sound source. Like for example, car engine running and car idling, we merge it as car. Buses and truck, we merge it as large vehicles. Right? So open source audio data set, you can all download free of charge. And it's not only these groups that you see in this slide, it can be more than that. You can always click on this audio data set, you can find a lot of these data sets. And we also probably want crowdsourcing of data set, but there's always a problem because annotation process is time consuming for large data set. And you will find that some of these individual collecting some of these data set can be quite subjective. They may not be very accurate. And also the label is very noisy and unreliable. So this is what I mentioned, the label noise. Sometimes we need to make sure that we label the data set that we collect correctly so that we can have a good data set, because rubbish in and rubbish out. So for evaluation of metrics, I think these are all the common ones that we use to measure the system performance, the accuracy, F1 score, error rates, the average precisions and mean average precisions, receiver operating characteristic, in short ROC, or even the corresponding area under the curve, AUC, and the equal error rate, ERR, and also the area under the precision recall curve, AUPRC. Okay, so there's many ways that you can measure the system performance. But there's also other considerations that we must bear in mind, the trust regulations and human-in-the-loop AI. Because how we trust the AI, okay, the adoption of AI, okay, is whether the citizen trusts these systems. So there's a public trust, and we need to make sure that it's safe, more reliable. So we must put human in the loop. Okay, without human in the loop, there's no trust. And there's also social responsibility of all the programmers to make sure that the AI is safe and is robust, and people were able to use it and they will feel safe. Okay, so human in the society in loop is very important, because we always ask why the result, why you reject these results, why do you think that how do you get the 75% or 55% accuracies? So the stakeholder must co-design the AI algorithm to encourage more responsible research innovations. Okay, so we need to also make sure it's interactive, so that people can try to make sense and try to explain, okay, on some of the AI, and to be able to know that the model this error and uncertainties. Okay, and the quality of intelligence system, you must have a good qualities, centralized data collections, and we need to maintain so that people can access it, and we must be able to describe the measurements data set correctly, And most important, as I mentioned, put human in the decision making, because most of the time the AI result is very biased. All right, so we need to implement fair for practical purpose. You must be able to find, you must be able to assess, you must be able to interact or give chance to interact with human and other systems. And most importantly, we must reuse your data. Okay, so I will say that explainable technique is very important, because we do not want the human to be blind by the AI results. And with that, I leave with some challenges, that how to predict when the method are going to fail or work, how to handle the data collection, how to prevent misuse of this method. So how do you know that you do not train on personal data that we do not be aware of? So this is a very important some of the questions or challenges that we have. So in conclusion, I think that most of us will work in less structured class data set already, and we have a spatial kind of these audios, and we will also have audio, video, and other modalities, and also joint data collection platform. How do we classify it robustly under weekly label data set? And we are looking more towards the transfer data or transfer learning, because of the lack of resources, meaning the computing resources. And also active learning. Okay, so this is something that we want to do as well, because we want to select which data point to queries for labeling, rather than just random or ad hoc approach. So with that, I have some past publication in the area of AI, transaction IEEE, or in audio, speech, language processing, IEEE access, and more onto the AI journals like soft computing, advanced engineering informatics, and also the neural computing and applications. And also I published in some conferences for me to actually network with some of the fellow researchers. So with that, I think thank you very much for your time. Thank you.